Now that you've been able to draw a Mohr circle and calculate the radius, a lot of problems ask for the principal stresses and or the maximum in-plane shear stresses associated with the given state of stress. And that gives us information associated with how the material is going to fail at that specific location on a structure. The principal stresses are the maximum and minimum normal stresses associated with an element. And in Mohr's circle, that is just here is the maximum normal stress, sigma 1, and here is the minimum normal stress, call that sigma 2. And a lot of times this is referred to as the major, and sigma 2 is referred to as the minor. You will notice here at this point that the shear stresses are 0, which means that this is in a pure normal stress state. And so if I want to calculate sigma 1, since I know this point C is sigma average, 0, sigma 1 is just sigma average plus the distance to that point, which is the radius of the circle. And then sigma 2 is sigma average minus the radius of the circle. Another piece of information that's important for me is the angle associated, or the angle of rotation I need to get to these principal stresses, or to orient my element in the principal stress state. And that angle is right here on Mohr's circle. This, I'll call this alpha. And alpha, I can use any trigonometric relationship associated with this right triangle. And so if I use tangent or inverse tangent, this will be tau xy over sigma x minus sigma average. And the angle associated with sigma 1, theta p1, is alpha divided by 2. And the thing we have to remember is that whatever angle you rotate in Mohr's circle, you rotate half that on the element. So theta p1 is equal to alpha over 2. And because we would go from 0 degrees here counterclockwise, this theta p1 is also counterclockwise. We can also calculate the angle associated with sigma 2 from, again, this is 0 degrees, and that angle would go right here, and I'll call that beta, and this beta is just 180 minus alpha in Mohr's circle, which I can calculate theta p2 as just beta over 2. In order for me to get to sigma 2 from theta equals 0 degrees, I've got to go clockwise, and that means this theta p2 is equal to beta over 2 clockwise. So if I want to draw the stress element in its principal stress state, I remember that theta equals 0 was established as horizontal. This was theta equals 0 degrees. And to get to sigma 1, I needed to go alpha over 2, or theta p1. So this angle associated with this sigma 1 would be here. This would be theta p1. And I would draw a line perpendicular to this right here, and the rest of the box, or the square. And this theta p1 would be pointing to my sigma 1 value. So I would have a stress here, sigma 1, and because according to the way this graph looks, sigma 1 is a positive number, so I would have it drawing in tension. There would be an equal and opposite on the other side. And then sigma 2 is also positive according to the way I derived this here. And so sigma 2, which is 180 degrees from sigma 1, would be 90 degrees in Mohr's circle, so this would be sigma 2. And in case you're wondering, this theta p2 would represent the rotation from 0 degrees to here. For the maximum in-plane shear stress, you can follow a similar process. The maximum in-plane shear stress is, as per definition, the largest shear stress associated with the element. And in this case, that would be at the tops and bottoms of Mohr's circle. So here, right here, this is tau max. And in fact, the coordinate for this is sigma average comma tau max, or tau, right here. And this is a distance r, the radius. And as you can imagine, tau max is equal to the radius. And sigma average we've already calculated. And the angle to get to this maximum in-plane shear stress from the theta equal to 0 degrees is this angle here, which I will label phi. And phi is equal to, I have a couple of choices. I had previously calculated this angle right here, alpha. So I could just do 90 degrees minus alpha. This is the angle I need to rotate clockwise in Mohr's circle. So on my stress element, theta s, is equal to phi divided by 2. And because here in this example or in this derivation I go clockwise, I'm also going to go clockwise here. And my stress element will look like this. From theta equals 0, I will rotate theta s. This was theta equals 0 degrees. And again, using this new line, I'm going to draw my stress element. The first line I'm going to draw is a line normal or perpendicular to that new axis, or the theta s axis. And from there, I will draw a square. Hopefully that looks square-ish. And now I have at this location here on this theta s, I have a positive shear stress, which would be on the plus face going plus or positive y direction here. I'll draw the rest of the shear stresses out. And the normal stress associated with this point is sigma average on all sides, because here even if I look at this side over here, this point also has sigma average, and that means that I would have a normal stress on all sides. Alright, so those are the essential elements of Mohr circle, especially when it relates to principal stresses and maximum in-plane shear stresses. And hopefully this was useful. Let me know if you have any questions. See ya.